And hi, everybody. It is AER 110DE/WX. That is the weather portion of Intermediate Aviation Concepts. And today we are going to be looking at thunderstorm activity. That is today's lecture 6, the 6th weather lecture of this series. And so we'll start off as we always do with a good look at the current weather. And it's been very, very nice. There has been some low cloudiness along the coast, not a lot. You can see snow in the high Sierra, otherwise just clear skies. Let's take a look at the mid-level water vapor here, and you can see some very dry air. This yellow is dry air. It's sort of encompassing the entire region right here. You go to low-level water vapor, it's probably even drier. There it is. You can see just nothing but dry air. So we'll go back to just regular satellite shot and take a look at some of those clouds down in the Los Angeles basin. Here you can see this interesting little effect here. You can see some waves coming from the east-northeast to the southwest right here, and it's beginning to show some down lee side drying here. This is, I believe, St. Nicholas Island, and that's not uncommon to see that. You can also see a little line of dry right here, which is coming from the coast. It's moving westward into the Pacific Ocean right there. And just a little bit of scattered cloudiness. Doesn't look like much. In fact, I'd like to see what we have here. Let's look at the current scenario. In Bakersfield, of course, just nothing but clear skies, 69 degrees. Along the coast, we're looking at higher dew points. The dew point in Bakersfield is 35, which is very dry. But the dew point along the coast is in the 50s. I'm sorry, the 50s, pardon me. And all the way down to San Diego. Are there any clouds there? Looks like there are some. 2,800 scattered and 25,000 scattered. Over in the Phoenix area, just a few high clouds. Let's see, 22,000 and 25,000. Yeah, Sky Harbor is always good about having multiple cirrus layers and either few or scattered. So there they are. All right, so as far as the past couple of hours, let's take a look at that. We will go back and look at, I don't know, the last 12 hours and expand for this area. We're going to go ahead and include the TAF. So here we go. So in Bakersfield, skies are clear. Winds are west at 9 knots. You can see it right there. Temperature, as mentioned, 21 Celsius, which is 69 degrees Fahrenheit. And the forecast is nothing but clear skies. We'll see winds out of the northwest this afternoon, 300 to 12 right down the runway. And then it goes pretty much light and variable after 3Z. In Oxnard, however, there were some clouds this morning. And here you can see, I guess the lowest is right about here. Right about there, 2,100 overcast, good visibility. So there was some stratocumulus clouds, or stratus actually. And the forecast, and they've gone clear now. Let's see, they broke out right here at 1806. So a little after 11 o'clock this morning, it cleared out. Now it's completely clear. And the forecast is for this. It looks like it'll clear out 20Z, which it has. And then we get back to some May gray. Now we can say it, now that it's May Day. And you can see 1,000 broken there. So kind of a low marginal VFR right at the border of IFR. San Diego, do we have any ceiling? We did. We had a ceiling here. Let's see. The lowest ceiling was right about here, 2,200 overcast. Very similar to the 2,200 overcast here in the Oxnard area, 2,100 actually. So the clouds are all based at about the same spot. And looks like they clear out in the afternoon, and they cleared out in San Diego right here to VFR at 1618. And I'll bet you, and I even mentioned this last time, that sometimes the forecast gets so predictable that they will actually predict a change down to the half hour. And that's the case here. So here's the San Diego forecast. It's a 30-hour forecast valid from 18 to 24Z, which is the same as 00Z. Few at 3,000. And then we see a ceiling here at 1,800 feet. But look at this. Look at the time, 16:30. All right down to the half hour. They forecast, the good folks at the National Weather Service there, that it will break out to VFR. So right down to that. And again, when we get into this diurnal, this daily pattern of clouds in the morning, clearing in the afternoon, then it happens again and again and again, and there's just no change in the weather, it can be very predictable. It's one of the most predictable things. So just curious here, what time did it clear out today? So we were 2800 broken at 16Z, and then right here at 1618, it went VFR. All right, so that's basically what they're saying, 1630, just to nail it down to the nearest 30 minutes. I suppose if they were really avant-garde, they could have said in the forecast here, 1618. Not that it would have happened then, but I mean, they can. And Phoenix, just a few high clouds here, a few high clouds there, and basically clear skies with a diurnal wind pattern. So we have westerly winds in the afternoon. You can see right here, 270 at 9. And then in the middle of the night, right around midnight, it goes easterly, 100 at 6. And then at 20Z in the afternoon, it's right back to 260 at 6, a westerly wind. Is that in fact what's happened? Well, if we look here, you can see here's that easterly wind at 12Z this morning. And it was light easterly as far back as 9Z this morning. And right now it's beginning to shift. So not only do we have diurnal clouds, but we also have diurnal winds, meaning that they have this daily cycle of going one way or the other. All right, so back to this, and nothing but clear skies. What's going to happen? Well, there is a low pressure system. Let's see if we can find that low pressure system. We'll go over here to here. And it's probably this one right here, making its way across the central Aleutians right now. If we look at it in mid-level water vapor imagery, it's this one right here. This low pressure system has been forecast to dive down into California over the weekend. And this is Wednesday as I record this. So we're talking 1, 2, 3.5 days from now. So let's see what the model says. All right, so the model is going to take that low pressure system. We'll do this, and right there it is. You can see it. It's coming into view right there. The time is up here in the upper left-hand corner. That's 21Z on Saturday, so that's Saturday afternoon. And then it brings rain into Kern County right there at 3Z Sunday, which is Saturday night at 8 p.m. So Saturday evening, it looks like there's some rain. It continues into the overnight time frame. It continues right up to 12Z on Sunday, and then after that, it's pretty much gone. And that's it. Question is, how much rain are we going to get? So let's look at the quantitative precipitation forecast. I call it the QPF. And what does it say? Well, let's see. So it gives, and we'll put the cursor here, it gives a couple hundredths of an inch. Up in the mountains, a little bit, well, a little bit more, 32 hundredths. If you go way up here, well, like 3 inches of rain in the high Sierra, which will all be snow. Speaking of snow, let's see what it says for winter weather. We're going to look at the total snowfall. It's a 10-to-1 ratio. And what do we have? Well, we have a little bit of snow right here. Looks like 2 inches in the Tehachapi area, perhaps. Okay, that is the GFS. That is the Global Forecast System, the American model. Now we're going to switch back to regular precipitation and all this. Now we're going to check another model. Let's check out the European model and see if it concurs, see if we have consensus and agreement in the models, because when that happens, then we have higher confidence if all the models are saying the same thing. And these models, by the way, the last class I talked a little bit about introduction to computer models. Every different model, in other words, the American model versus the Japanese model versus the German model versus the European model, they all basically are forecasting the same parameters, but they have slightly different equations. They have different methods of forecasting into the future, what will happen, different processes of, and it gets very, very detailed, but there are differences. So when all of them are still saying the same thing, that gives you confidence, even with all the differences, that that something is going to happen. So here comes the rain. And that is Saturday at 15Z, so Saturday morning. Now we go into Saturday evening, and right there we've got precipitation in Kern County. Looks like 3Z Sunday, which is 8 o'clock Saturday night, and it does continue. So that's very consistent. And then we go into Sunday and beyond, and we're done with precipitation. Okay, so those are two models that are saying it. And how much rain is it giving us? Let's look. So we go into the future here, and let's see, what do we have? Looks like maybe a little bit more, especially down here. Wow, definitely a lot more with the cursor right there in the Fraser Park area. Let's see what it says as far as winter weather. Now I'm curious. Let's see. We'll go to Kuchera. We'll see what the total snowfall is. And, well, not much. Okay, so this doesn't give as much snowfall, probably because the air mass is slightly warmer. All right, so we'll go back to what we were looking at before, and we'll try a couple of other models just to see if there's any more consensus. We'll go to the Canadian model, which is a pretty good model here, see what it says for us. And there's the rain. Okay, so it brings it in right there, and the time is, now this is a little bit later. So here is late Saturday night before the rain gets here, and that is a 12Z Sunday morning, which is 5 a.m. And it get a little bit of precipitation, not a lot. All right, that's the Canadian model. The German model now. German model, what does it say? Let's see, it's giving us definitely some precipitation. So all of the models are in agreement that Saturday night it will rain. Not a lot, but there will be some rain and probably some pretty gusty winds too. All right, and just to confirm all that, let's see what the MOS says. So here's the MOS model right here. This is for Bakersfield. Here's Thursday, Friday, Saturday, Sunday, and we're looking at the probability of precipitation. That's right there, 56%. And it's saying category 2, which means that we'll get about 1/4 of an inch of rain. And yeah, I pretty much concur with that. What does the national blend of models say? This will be, if this says that we're going to get some rain, then it is it's concluded. Colorado will also get Oxnard and San Diego, KSAN and KPHX Phoenix. And here we go. All right, so for Bakersfield, it says that there is a 30% chance for rain. This would be Saturday night, but it doesn't give us any precipitation. The Q right there, this Q line, that would be the quantitative precipitation. It doesn't say anything at all. So that means probably not. In San Diego, let's see here, the chance for rain is nil. Here's 5%. In the Oxnard area, what do we have? Here's Oxnard, and their chance for rain also only 8%, not very high. And Phoenix, of course, no rain at all. See what the temperatures are going to be in Phoenix. We get up to 97 degrees for Saturday, and then it cools off a little bit after that. And temperatures for Bakersfield, by the way, let's see, we get up to 84 degrees on Friday, and then the high on Sunday is only 68. So we'll definitely be cooling down. So that is what we are looking at from this system here. And the computer models have to take all of the data that they have way out here in the Aleutians, and then decide what it will do, 3, 4, 5 days from now, downstream here, and it takes everything into account. All right, let's look at a couple of other things here. We have some pretty big severe storms potential. We're talking thunderstorms today, and here is the current convective outlook. And it shows there's an enhanced area of potential risk for thunderstorms from about the Concho Valley of Texas all the way up into far southwestern Kansas. So this is an area that's had some pretty big thunderstorms before. And here's the summary. Greatest threat today is large to very large hail, severe thunderstorms, and a few tornadoes. So it's more severe weather than it is tornadic activity. And these are the people who, this guy right here, John Hart, he was actually, believe it or not, back in the late 80s, he was an intern of mine, and he has become one of the leaders at the Storm Prediction Center in Norman, Oklahoma. So I'm very proud of John Hart. He lives right there and been there for a long time. Anyway, that's today. Here's tomorrow. Still a slight chance right here, not as big, not an enhanced chance, but a slight. And then going into Friday, looks like a marginal shock right here. So this again is the convective outlook. That's Sunday, Monday. Okay, so Monday there is a chance right there. That's day 6. This will be this area right here. As that low pressure system that's going to bring us some rain on Saturday night. It'll be here Saturday night, and it will kick out into the southern and central plains on Monday with severe storms. Now, it sounds to me like somebody is on the call here. So let's see, who do we have? All right, Ivan.
Yep.
How are you today?
Pretty good. I won a lucky prize, just finished class and got myself some lunch. So, a good day and a good way to start off the day. And just
Yeah.
pretty
What
fun.
sort of lucky prize did you win?
I won peanut M&Ms and Snickers.
For what?
It was just here at CAU. There's like a weekly question, I guess, and you answer it and you put your name in the box. And I guess I got pulled. So then I was like, oh, let's go.
So what was the correct answer?
There wasn't a correct answer. It was just it's more of your opinion. It's like, what's your favorite color? Where would you like to go? What do you do while you're studying?
I see. Okay. Well,
Yeah.
very, very good. Well, congratulations on winning that. It's going to be a good day for you.
Yeah, thank
All
you.
right, we'll get back to what we were looking at here. We're looking at some severe weather, which is going to be popping up in the middle of the country. So let's look at a satellite shot for that part of the world. So here we go. We're going to go here. We're going to put this into motion, and then we're going to go to where all the action is, which is right here. Okay, now this is interesting. I see a couple of things going on here. You can see some thunderstorms developing here around Fort Stockton, but you can also see this interesting little kind of bow-shaped line right here. And there's all sorts of just fascinating things if you just look at this satellite picture. Up here we have some appears to be gravity waves. We have some cloud streaks down here. We have this interesting little bow-shaped something. The question is, what's causing it? It looks like it's moving to the north, the west-northwest. So if we go back many, many hours, that will go all the way back to here, we might get an idea. This is interesting. This is overnight. So there was some thunderstorm activity over the Red River Valley here. And the thunderstorm updrafts, they are very strong. They hit the tropopause, the top of the troposphere, and then they bounce off the tropopause. It's like hitting the ceiling, and then this wave will go out in all directions. And that's probably what we saw there. And this is also yes.
I hope you don't mind. This I'm just kind of curious on this question. Like, I know for to create like a thunderstorm, you need lifting, moisture, and unstable air. But what causes like the lightning? Like the like the thunder, or like what is causing that?
What is causing lightning? Well, that's a very good question, because you can't have a thunderstorm without lightning, because lightning has to happen first. That causes thunder, then you have a thunderstorm. Well, I'll get into that. In fact, I might get into that like right now, just very quickly. Let me come over here and we will add, because we're talking thunderstorms today. And you had mentioned those 3 ingredients. There are actually 5 ingredients. There are not 3 ingredients. There are 5 ingredients, and that's what I want everybody to remember. Well, let me go ahead and do this right now. We'll do this and this, and I'm sure you can see all this. So this way I can actually write. So what happens is that here it is. Here's the ground down here, and we have thunderstorm up here. There it is, and we have the freezing line, which is right about there. That's 0 degrees Celsius. So we have updrafts, and then we have ice, which develops in the upper part of the thunderstorm. In fact, you can't have thunder and you can't have lightning first without ice. So the ice is made up of little plates of ice. They're not snow crystals, they're ice platelets. And so with the strong updrafts, they sort of brush against each other and they strip electrons off. And so what happens is that we get a positive charge in the upper part of the storm. And then at the base, we have negative charge. This is the electric polarity, okay? So normally the ground is negatively charged. You probably heard that. But whenever there's a thunderstorm, there is this shadow under the storm of positive polarity. So we have positive on the ground, and that is a shadow which is caused by the negative polarity of the base of the cloud. And then we have all this positive in the top. Do you see that? So we have positive and then negative and then positive on the ground. Well,
And
go ahead.
And this positive is created because the electrons, the ice is getting rid of the electrons. Like it's
stripping the electrons of off of the water molecules, and so
why
it's
is it
very
doing that?
similar. It's very similar to if it's a cold winter's day and you have like a rug, like a shag carpet or something like that, and it's very cold and dry, and you just shuffle your feet along that. You will actually do the same thing. You will strip electrons so that you can actually touch your sister's ear and it'll pop, you know.
Right.
That happens in the winter time. And again, it's the winter time. It's ice. That is when you can strip electrons. So you have to, and that's basically what happens. It's just this stripping away of electrons. So we get a positive charge in the top up here in the ice, negative at the base. And at some point, the polarity becomes so intense that it has to balance itself out. So what happens is that there's like a little streamer that's coming down from the base of the cloud, and it's looking for something sharp that it can connect with and can set up a flow of electrons. And then the electrons, once that happens, flow up into the cloud. Yeah, lightning actually goes from the ground into the cloud, not the other way around. And then you have this very intense flow of electrons, which glows very brightly. It's called lightning. And the flow of electrons is about the size of my thumb right here. That's it. But it is so hot. It is so hot. It is 50,000 degrees Fahrenheit. 50,000 degrees Fahrenheit. That it causes the air immediately around that little flow of electrons to expand, because anything that warms up expands. Things that cool off contract. You know that, right? So here's the thing. So when it expands so fast. It's expanding faster than the speed of sound. And so this expansion that you have here due to the flow of electrons, lightning, is basically a sonic boom. It's a sonic boom caused by the rapid expansion of the air. Okay?
So is that a microburst?
No, it's not a microburst. We're talking about what causes the lightning and what therefore causes thunder. So thunder is a sonic boom caused by ice, which strips electrons in the top of the thunderstorm. So the tops of a cumulus cloud have to reach up above the freezing level before anything can happen. You're not going to ever have lightning if you don't have ice in the top of whatever it is, even if it's a volcano. So some big volcanoes will erupt, and sometimes you'll see lightning around those. But that's only because the tops of the volcanic ash actually get up above the freezing level. And then you'll get that. Plus, sometimes you can actually get that same effect of stripping electrons just from the very strong updrafts and the fact that it's volcanic ash, not ice necessarily. But generally, you have to have ice. All right, so did that help you understand what causes lightning and thereby what causes thunder?
My only question is, why doesn't the negative electrons go to the ones positive, like the ones above it? Like, isn't that a shorter distance?
Oh, why doesn't the lightning come down in? Well, it does. It does that too. We have lightning. In fact, if you look at a meter observation, in cloud, cloud to cloud, cloud to ground, and the cloud to ground is actually ground to cloud. But a lot of cloud to cloud lightning. You can have cloud to cloud lightning all the time, and in that case, that's what's happening. Plus, sometimes you get what's known as a positive strike, and that is a strike way out over here where the ground is negative. Remember, there's a shadow under the storm itself, but usually
Right.
the ground is negative, and sometimes you can actually get this lightning bolt that goes from the top of the cloud, like 25 miles away over here. That's called a bolt from the blue. Maybe you've heard that term before. And that's what's really dangerous, because if you're standing out there and all of a sudden lightning strikes and you don't even know there's a thunderstorm nearby, well, that's a big surprise. That's a big surprise. Okay. All right. So let's go ahead and discard that. And we're going to get back to what we're talking about here. So this was rather interesting.
Right.
You'll notice this this dark line right here. In fact, let me go ahead and just go into shortwave imagery. Do you see this line of dark right here? It's moving to the north. That is actually the dew point. So over here where it is lighter, the air is much drier. But at night, after we've had the thunderstorm activity over here, the dew points will actually rush back, and you can actually see it. It's like a moisture front right there. Do you see it? It's
Yeah, I see it. I see it.
So yeah, if you were to look at, let's go ahead and look at that right now. So we're going to go over here to Texas, and we're going to look at the dew point. So the dew point is the lower left number there. So the 64 there is the dew point. There's a 70-degree dew point at Childress, Texas, but right over here in Plainview, the dew point's 43. That is a lot drier. And if you go over to Clovis, New Mexico, it's 17. Here's a dew point of in El Paso of 10. So that is a very, very sharp line. In fact, right here, you can see in Fort Stockton, the dew point is 61. And over here in Van Horn, the dew point 17. So that is a very, very sharp line. In fact, I think I can show you. Let's go to
And the line is causing the decrease in the dew point, correct?
The lightning, did you say?
No, the line,
Oh yeah, the line. Right.
Yeah.
Yes. Let me go ahead and look at this. We'll take a look at dew points. And we're going to go over here to 12Z. We're going to find this regional area right down here, right here. And we're going to look at just dew points. Here's dew points. Okay. So notice the dew points. 60-degree, here's 70-degree dew points there. And as we go into the future now, you can see how that all changes. There's that sharp dry, it's called a dry line, with the dew points in the 60s in the moist air and only teens over here. So that is a very, very sharp dry line. And then you can see it moving back up. And then we're going into the future here, and you can see that dry line going back and forth with very high dew points in the 70s over much of southeast Texas, and dew points in like the single numbers over here. There's a 4-degree dew point there in Van Horn. And so that is that's rather interesting. Let's see here. If we look at here, look at this. So here is another look at that. You can see thunderstorms will develop right along the dry line, right there. There you can see it. This is right along the dry line there. And then it moves to the east, big thunderstorms moving through Houston. And then we're pretty much done with it. So very interesting. What was that?
Oh, it is because the dew point has to do with icing, right? So then the icing is the reason that is another cause for the thunderstorm, correct? Right?
No, dew point is simply the amount of moisture in the air. It has nothing, nothing definitely to do with anything other than how much moisture is in the air. Is there a lot of moisture or not? And so let's see. So the dew point, and here you can actually see the wind barbs. Yeah, the dew point, for example, our dew point, let's see what our dew point is here. So we'll come over here to our area. So our dew points are much higher right along the coast. So that's because of the marine layer right there. And as we go into the future, let me just do dew points, just dew points. All right, here's the dew point. So looking into the future, let's see what the dew points do. They don't change much. They're pretty dry. Look at these dew points over Nevada, -9. Okay, so that's very, very dry. The lower the dew point, the less water vapor is mixed into the atmosphere, right? That is, you don't want to look
at for thunder.
What was that?
And then so then less chance for like the lightning, the thunderstorm, you know?
Yeah, you
right?
have to have moisture, and that's one of the
Gotcha.
ingredients in the thunderstorm recipe,
Yep.
which we'll talk about
I
in just a
got
few
it
moments.
now.
But here you can
Yeah.
see very, very dry air in the interior, and there's that moist layer. Looks like some moisture moving down right there. I couldn't help but notice that. The moisture, you see the moisture coming into the Central Valley right here as
Yeah.
we go into here. It's coming right down. So there's moisture which is coming on down, but it's very, very dry otherwise. All right, so okay.
Um,
The
is there a certain
Yes.
threshold of dew point that like you would say, oh man, that's a thunderstorm right there? Or is it just probability based? Like is it if there's a if there's 50 dew if there's a 50 dew point, there's a 50% chance of a thunderstorm that day, or
That's a good point. Actually, no, there is a threshold. You know that it's really humid if the dew points are up into like the 70s or something like that. That's very, very high dew points are kind of miserable. Here's the dew points once again. So here's the dew points. There they are. So yeah, whenever the dew points are basically over, say 55, you can definitely feel it. If you get 70-degree dew points like this, or like here in the Gulf of Mexico, it's like a sauna. It can be very, very hot. But the temperatures, let me see if we have heat. Here's the heat index. So the heat index is the temperature, and then you apply the dew point. And if you do that, you can get very, very high heat indices. Like down here, right around Cotulla, Texas, there's 100. It feels like 100 degrees. It's not 100 degrees, but with those 70-degree dew points, it feels like it. So then you can see those thunderstorms coming across here and actually cooling things down a little bit. So let's see what we have as far as lightning flash. Okay, here let's look at a lightning flash. You want to talk about lightning? So here, this actually forecasts when the lightning flashes will be and what the flash density. In other words, flashes per square kilometer per 5 minutes. That's what this is right up here. So it looks like a lot of lightning there, thunderstorms for sure. And then it moves through central Texas and moves on out. Let's see if there's thunderstorms in other parts of the country. How about up here? Let's look up here. All right, so we're going to look at lightning uh, density. Big thunderstorms over Kansas there. It looks like it'll move across northeastern Kansas. So there's plenty of thunderstorm activity going on there. And does this actually have cloud tops? I don't think it has that. If we were to look, let's take a look at what's happening right now. We'll just actually go over here. We're going to go to, here we go. We'll do this. We'll go to this radar. I'm going to go to this one right here and look at what's happening with these thunderstorms just south of Midland. So these are the thunderstorms that are brewing right now. If we look at the thunderstorm tops, here are the tops. They're up there. The red right there is 46 to 50,000 feet. And is there any hail in them? Let's see if there's any red. Red would mean hail. And I don't really see much, not too much right now. But I do know that there will be some big thunderstorms later on. Here, once again, is that area. So this is just the beginning of what is going to be a very busy day for severe weather. If we look once again at the severe thunderstorms, we'll go ahead and look at the meso-analysis here of the southern plains right here. Okay, so here's that area. So currently, the most unstable cape. So we have there's a 4,000 cape. That's very unstable air here, over here. Let's see what the supercell composite is. So there's potential for supercells up here in the Childress area. How about the tornadoes? So there's a chance for tornadoes up here and also way down here in South Texas. And how about the hail size? Okay, so let's see, blue, white. So white is 4 inches in diameter. So a lot of hail down there. So a lot of really bad weather. And by the way, here is precipitable water. So this only looks at the dew point. You want to know about dew point. This can take the dew point and tell you how much moisture might be precipitated. So we have like 1 point. Now here's 2 inches down here. So flooding can take place in the Corpus Christi area. And yeah, so there's a lot of instability down there. All right, so
and
that is
what's the like the the weird colors, like the blue and the green, like the little patches? What are
These,
those?
this right here, that's
Yeah.
current radar is what that is. So there's a little, you're looking at that, there's actually a little, let's see if we can show it here. Oh, it doesn't show it very well. It's just simply where there are showers right now. There's showers right
Oh,
there. There's some showers that you
okay.
saw on the radar over there. That's all that is. That's the current
Right.
radar. That
Got it.
guy can turn the radar off by doing this, and now you don't see it at all.
Oh,
So
okay.
very, very unstable air down here. And if we were to look at the skew-T from, we'll pick a place. We'll pick Austin, Texas. So we're going to go to Austin, Texas. And right now they have a CAPE. You can see it up here in the upper right of 3,000. And that means that we have a lot of moisture. The temperature and dew point down here are the same. So this is a very, very moist layer. And you have to go above 6,000 feet before you get into any area where there's no moisture. And the winds are coming around from the southeast to the south to the west, which you will find in just a few moments when we talk about it, is one of the major ingredients in storms. So let's go ahead and start today's topic. We're going to get rid of this. Okay, so here we go with today's topic. And today we're talking about thunderstorms. And we're going to talk about hazards again next week. But today it's just thunderstorms. There they are. There's a big thunderstorm. You can tell it's a thunderstorm because it has ice in the top of the cloud. There's a big anvil cloud. You can see how beautiful that is. Look how nice that looks. And you can also see a very significant inflow. So here is the inflow into the cloud. Here is the anvil right here. It is actually up to the top of the cloud. Here's the overshooting tops right there. So we have a lot of upward motion. That's how you know it's going to be a thunderstorm. But how do you make a thunderstorm? Well, how do you make a cake? So here we have a delicious, looks like a red strawberry something something cake. And of course, there are ingredients. There's sugar, a lot of that, sugar and flour and milk, and don't forget the strawberries and everything else. So there is a cake cookbook recipe, how you make delicious cakes. Well, in the same way, there is a recipe for how to make thunderstorms. And everybody has heard some of the ingredients. In fact, you mentioned it yourself just a moment ago, Ivan, that there were like 3 things that make thunderstorms. But I am here to tell you there are 5 things, not 3. And even though I'm going to talk about the 5 ingredients, most of you are probably going to only remember 3 ingredients because you've read that in other places. But again, the correct answer for this course is that there are 5 ingredients. So let's look at those 5, not 3, those 5 ingredients. The first 3 are the 3 that everybody talks about. Instability. So instability means that we've got an unstable air mass. There's moisture that you have to have. We have to have a favorable vertical wind profile. And then the 2 that nobody talks about, but I am talking about, is you have to have a trigger, because you can have all of those ingredients in the thunderstorm cookbook, but you don't activate them. You don't put them into motion. They're just sitting there kind of latent. So you have to have a trigger, and then to keep it going, you have to have maintenance. So let's look at each one of these 5 ingredients in a thunderstorm. First, upward air currents. You have to have instability, which means that the air aloft needs to be particularly cold. So here is the typical environmental lapse rate. It's about 12 degrees per kilometer. And when the lapse rate is sharper than that, maybe it's 14, maybe it's 18 degrees per kilometer, then we're talking very, very unstable. If the lapse rate is slower, it's only maybe 8 or even 6 degrees per kilometer, then it is not nearly as unstable. So you have to have cold air. Now it cools off normally with height, but you have to have particularly cold air aloft, or you have to have particularly warm or even hot air. and you can include moist, very unstable air in the bottom, or you can have both. And usually you have both, and that is what brings about thunderstorm activity. You have to have instability. You have to have a reason for the upward air currents to develop. It has to be the bubbling up of less dense air into dense air. You're turning things over. Next up, you have to have moisture. That's the fuel for clouds and precipitation. No moisture, then you don't have any clouds. And if you don't have any clouds, you certainly don't have any rain. If you don't have rain and ice, then you don't have thunderstorms. So you have to have that. But the good news here, though, is that there is abundant moisture in the world. 70% of the world is liquid water, the surface. That only leaves 30% of where we live. So more than double of the land that we live on, more than double of that area is water. And of course, water comes from all different sources, from the Atlantic, from the Pacific, from the Gulf of Mexico, from any place where there is open water. And everybody did the first weather assignment in this course, which was tell me about the water cycle. So you know that there's a water cycle. So we have liquid water that becomes vapor. Then that vapor can blow over the land right here, and then it condenses under the ideal conditions. And then we have rain and we have thunderstorms. So you have to have moisture. No moisture, that's one ingredient that will veto thunderstorm activity. Next up, we have the favorably changing wind. This is the very, sometimes it's difficult to understand how this is important, why this is important. But if you don't have a favorably changing wind direction and speed aloft, you will not have the venue for thunderstorms. You might have all the instability and moisture in the world, but if you don't have the right winds, then you're not going to really have a significant thunderstorm. So here's the way it works. Think of this as being south and this as being north over here. And you have the low-level winds. And what happens is that at the top of this tube, let's call this a tube down here. It's a tube of wind. It's all flowing nicely. And at the top, you have winds that shift a little bit more. Instead of out of the south, they're a little bit more out of the southwest as you go higher. And then you go even higher still, and now the winds are out of the west. Well, that is causing this tube to actually rotate. You'll notice that the arrows here, they go, and you can see that they're rotating a little bit. And so as they continue to rotate, and if you're down here at the south end and you're looking down the tube, you're looking up where the winds are blowing, it looks as though the winds are blowing clockwise, like that. And they are. And so as you go up into the sky, so here are the winds. You're going to start off with a south wind, and then you're going to see a southwest wind, a little stronger, then a west wind up here. The wind is shifting clockwise with height. Do you see that? So that is what is an important ingredient. And you might say clockwise. Well, that whole thing's good. That's like a high pressure system, right? Did you have a question?
Yeah, so the rotation is happening because of the combination of winds, like coming together to one place.
Yes, the wind is the tube of wind from the south to the north is blowing as it does, but the top of the tube is being pushed a little bit. It's being pushed. It's being pushed a little bit more toward the east, and so that causes the tube,
Rotation.
as it is going from south to north, to actually rotate a little bit. It's rotating clockwise as you look at it from behind. So you're looking from the south to the north, and there it is rotating clockwise. But when that tube reaches something and it is then forced to go vertically, this clockwise turning right here, clockwise turning, will be looking as if it's counterclockwise if you look at it from above. And it'll look like a low pressure system. So let's see, I don't really have, I have pencils and pens and things like that. If you take a pen, and you turn it clockwise as you're looking from behind. So it's clockwise, and then keep it going clockwise, and then turn it vertically, and then look down upon it. It'll be going counterclockwise. That's the point. And so whenever these winds are being caused to spin clockwise as you look at it from the south, it'll be counterclockwise as you look at it from above once it is lifted vertically. All of that sounds somewhat convoluted, maybe a little bit difficult to understand, but just remember that the winds have got to shift clockwise with height, and that is favorable for thunderstorm activity. Winds shifting clockwise is called veering.
What happens if it does counterclockwise? Is that not good for a thunderstorm?
Correct. That would be just the opposite. So let me go ahead and erase this.
What would that cause?
That would cause downward motion. So if the winds are veering, and that would be shifting clockwise with height, that's favorable. If the winds are going the other direction, if the winds are starting off like westerly, and then with height they're going the other direction like that, so as you go vertically they're going this way, that's called backing. So the winds can either veer or they can back. There is no in between. If the winds are backing, that means that they are shifting. They're shifting counterclockwise. It means that the top of the little tube there is going toward the west, making it go the other way. And if that's the case, when this tube is then pushed vertically, then it will be looking like a high pressure system as you look at it from above.
Okay, so the clockwise is what causes the upward motion, right? And let's say, we create the thunderstorm. Now that it's dissipating the storm, right? Is it going to move counterclockwise since it's going downwards?
Mm-hmm. Yes.
Okay.
Veering winds with height cause thunderstorms or cause conditions favorable for thunderstorms. Backing winds with height do just the opposite. So if you are looking for thunderstorms, then you want veering winds. In fact, let's take a look here. We'll get rid of this, and we're going to go to this, and we're going to look at some more soundings. Let's go to, let's see, where we're going to go. Let's go to Midland, Texas. Okay, so Midland, Texas, we're going to go to this afternoon and see what the winds are doing there. Here we go. Okay, so the winds, as you can see right here, start off southerly, and now they are shifting clockwise with height. Do you see that? They're going southwest, and now they're getting very strong out of the southwest right there.
Right.
That is favorable for thunderstorm activity. Let's go to like Oklahoma City. OKC. So we'll try Oklahoma City and see what's happening there. So the winds are southerly, and then they become southwesterly, and that too is favorable for thunderstorms. Let's go to someplace completely different. Let's go to Albany, New York. I have no idea what's happening there, so let's see. So the winds there are pretty much all northwesterly, and they don't really change much at all. So that's neither here nor there. Let's go to some other place. Let's go to.
And then that would not be favorable because it's not coming in from the south and not coming.
Right, that's not favorable at all. Yeah. Let's go to like Seattle, Washington. So we're going to go to Seattle and see what's going on there. So the winds there go from southwest to like calm to northwest. So there's a little bit of veering there, but not a lot. Let's go to some other place. Let's go to you have a place that you want to suggest? Where can we go?
I only know KBFL.
Well, all right, we'll try KBFL. Let's try that. See what's happening here. All right, KBFL. The winds are northwesterly, and actually they back. They go from northwest to a little bit more a little bit here westerly. So here the winds actually are backing. They're going from 330 at 10 to 290 at 30. So they actually are backing right here. So that would be unfavorable for thunderstorm activity. Okay, well, that was great. All right, do you understand that, Ivan?
What happens if the winds are coming like from the other direction? That's unfavorable as well, right?
Right.
To the west, like if they're going to because that one's it's going to the east, but if we're reporting towards the west, that'd just be unfavorable because it'd be counterclockwise, right? Even if it was coming in from the south.
Yes, it is strictly how is the wind changing, not necessarily where it's coming from. Let's see what we have here. Here is an easterly wind. This is Key West, Florida, right at the southern tip of Florida. We have an easterly wind right here. You can see winds 100 to 10. There's a northeasterly wind. So actually the winds are backing right there. They're changing with height counterclockwise. So no significant thunderstorm.
Oh, I see what you're saying now. I think I get it now.
Okay. So how does the wind change as you go vertically? Does the wind change clockwise or counterclockwise? And
Clockwise,
in this case right here, what is it doing? It's going from east to northeast to northwest. So how is that changing?
counterclockwise.
That is counterclockwise, yes. And that
Yes,
is not favorable for thunderstorms, yes.
yes.
But if
Gotcha.
we, if we
I thought that it was the direction that matters, but it's the I guess it is also the direction, but not like the way I was thinking of. But I see it
right.
now.
So here we're in Midland, Texas again. So it's going from south to southwest to west, right there. And that would be changing clockwise, which is favorable for thunderstorm activity.
Correct.
Okay, excellent. So we understand that. That's a tough one to understand, but I think you got it. All right. So there it is. Once again, you can see what I just mentioned before. So with this here, this is good for multi-cells and squall lines. You can see the wind shifting, going from south to southwest. That would be veering winds. And this is unorganized over here. We go sort of all over the place. But supercells, they go from southeast to southwest to west southwest, and they increase with height. So they're getting stronger as you're going up. That's the perfect scenario. Next up, you have to have a trigger. That is the push to activity. Again, you can have these three things up here that everybody thinks about, but if you don't have something to light the fuse, it just won't go. So you have to push to activity. And to do that, you have to have, here's a dry line right here, or you have to have a frontal system like this. This is called a composite chart. This is something that severe storm forecasters use all the time to figure out the areas where the severe weather will be. In fact, you saw it earlier. A composite chart like this was used, let's do this, to come up with the current, that's right here. So here's the current outlook, and they used a composite chart to determine this is the area right here. By the way, we do have a watch which has been issued. So there. So here we have a severe thunderstorm watch for southwest Texas, large hail up to 3 inches in diameter. And this was issued by my friend John Hart right there. So severe thunderstorm watch is along 60 miles east and west of a line from 55 miles north-northeast of Big Spring, Texas to 40 miles southwest of Dryden, Texas. Okay, so there it is, this area right here, and they'll be watching that valid until 9 p.m. Central Time tonight. But that's going to be just the first of several watches that are issued for later on today, because this is the convective outlook right here, and this whole area is under the gun. This is the enhanced area. We have a slight risk area that goes all the way up to about Omaha, and then around that we have a marginal risk area. So you can see that. Yes, did you have a question?
Right. So what causes the difference in thunderstorms?
The different risk?
No, like there's different kinds of thunderstorms, right?
Yes, and we're going to talk about that in just a moment. Well,
Okay.
let's just
Okay.
get into
Sorry.
that then. So no, that's fine. So here we have the composite chart, which is used to determine where the thunderstorms will be. And in this particular case, you can see thunderstorms are expected to develop. Here's the upper level trough. Here's the upper level ridge. Here's the surface low pressure system. Here's the polar jet, the subtropical jet, the low level jet. So this little area right here is where the bad weather would take place. Finally, you have to have maintenance. You have to keep this thing from dissipating because thunderstorms may pop up, but then if they move into an area that is very stable, let's say the vertical wind profile is unfavorable, then the thunderstorms will stop. So you have to keep them from going. So once again, we have 1, 2, 3, 4, 5. Not 3, but we have 5 ingredients in the thunderstorm recipe. Instability, moisture, vertical wind profile, which we spend a lot of time on, and I'm glad. And those are the 3 that you have to have. And then you're not going to have thunderstorms though if you don't have a trigger and maintenance to
So
continue.
I understand everything but like trigger. Could you go back to trigger?
Oh, the trigger. Okay,
Right.
so the trigger is you have all of the. In fact, we can look here. So let's go back and look. So we're going to come over here to this and take a look at. Let's see here.
Like, is the trigger just the fronts? Just you need fronts to trigger it? Is that what the trigger is?
Yes, you do need fronts, or you need perhaps a trough of low pressure or something. So here we will have. Let's look at severe weather. So here's severe weather. We're going to look at the lifted index. So here's the lifted index, and this is a representation of how unstable the atmosphere is. So we have plenty of instability here, but that doesn't mean that we're going to necessarily have thunderstorms. So we continue to see the very ripe air just ready to go. Here's the lapse rate. So wherever the lapse rate is very, very significant, you might have a lot of thunderstorm activity, but you won't have that thunderstorm activity until something comes along to cause it. So here is that the thing. We've got, in this case, winds, which develop. Let's go back right here. Okay, so we have a trough, and we have winds right along the dry line. The time here is 00Z, so the heat of the day is strongest. And so the thunderstorms will develop, and then they will move to the east because that is the direction that they are being blown. But they will continue right into the night. Here it is, middle of the night, and it's raining hard in Dallas. And it all started over here, right here. And you saw just a moment ago that in satellite imagery, and we'll take a look at this. Let's do this, and we'll look at this. Okay, so right now we have all of the unstable air here, but only down here. This is where the trigger has developed, is right along that dry line right there. That has caused the storms. Plus, you can see some
So
other high cirrus clouds coming across here, and that may be a little wave, which is also causing the thunderstorms to develop. So there's something that comes along that says, okay, begin. And right here, you can see a new one right there. Looks like a little thunderstorm developing just south of Midland.
and it doesn't have
Yes,
to be a combination, right? It can just, like you said, it can just be a single dry line or a single front or a
sure,
single
sure.
trough.
Yes, it can be whatever it is, but there has to be something that starts the process. It could be a
Okay,
front, it could be a trough, it could be a dry line, it could be a wave coming in, a loft. It could be one of several things there. See if I can
gotcha. Thank you.
find this here. This is not working for some reason. Oh well. All right, so yeah, you have to have that trigger. All right, so we'll come back to this and this. And there's the trigger. Okay, so now we're going to talk about the 4, count them, 4 different types of thunderstorms. There are 4 types of thunderstorms. And you'll notice this is a great illustration here. You can see that the lightning is actually going up into the cloud. You have like little tributaries here. In fact, if you look at it here, you can see that the lightning is going this way into the cloud. You can tell because we have tributaries. It's just think of like little creeks that are coming into a big river, you know, and so the flow is up. And over here, you can also see the flow going from over here, going this way. This is cloud to cloud lightning right there.
Yep.
All right, so we have 4 different types of thunderstorms. And so here's the first type. We're not talking intensities of thunderstorms. We're talking types. So first is the diurnal thunderstorm, and that is the thunderstorm that develops during the daily cycle. This is your plain Jane air mass garden variety thunderstorm that you might see in June or July across the southeastern United States. So it comes in 3 different parts. We have the towering cumulus stage, and in this stage we have the updrafts. You'll notice the little isotherms there, meaning that the middle of the cloud is warmer than the sides. So you have a warm updraft. That's the cumulus stage, or the towering cumulus stage, or phase, you could call it that too. That's the first. The second over here, we have the updrafts. You can see the temperature line right there showing updrafts. But then we get to a point where the cloud droplets all begin to coalesce together. They form bigger droplets and bigger droplets. Plus, we get ice up here because we're way above the freezing level. So a lot of things are happening. And so these great big drops start getting pulled back down to the ground because of gravity. So gravity will pull these giant raindrops down. And when that happens, all of these raindrops that are falling down will grab the air and cause a downdraft. So now we have downdrafts, and we also have, there's the isotherms right there. So this is cold. So we have cold downdrafts at the same time that we have warm updrafts. So it's all happening at the same time. That's called a mature storm, the mature phase. Okay, and then that's the second. Finally, the third phase is called the dissipating stage or phase, and it's mostly downdrafts. We have a little bit of precipitation. You can see it's mainly cooler in the middle, a little bit of updrafts way up here at the top. So those are the 3 different phases or stages of the diurnal thunderstorm. Diurnal simply means a daily cycle. The sun comes up, the sun goes down, then the sun comes up again. You wake up, go to work, then you go home, go to sleep, then you wake up and go to work again. And that is a diurnal cycle. The second type, and this is type number 2, is a synoptic thunderstorm. Now, a synoptic thunderstorm is a storm that has all of the ingredients that we talked about. There are 5 of them. Okay, so Ivan, what are the 5 ingredients to make a thunderstorm?
Unstable, moisture, uplift, you know what I mean, and then trigger, and then maintenance.
Right. Now you said uplift, and what you should have said is favorable vertical wind profile. That is
Right.
the shifting of the wind. A lot of people say uplift, but uplift is the same as unstable. So that
Okay.
third one is the favorable vertical wind profile. It's got a lot of words to it, but it is that change of wind direction clockwise, veering. That is that. So we have all of those ingredients in a synoptic thunderstorm. And the thing about a synoptic thunderstorm is that it is formed by synoptic features. Synoptic means like the headlines, the lows, the highs, the fronts, anything that you can put on a weather map, saying this is the weather right now, like a cold front or an occluded front or a dry line, or even just a jet stream. Those are called synoptic features. And so any thunderstorms that are caused by synoptic features are called synoptic thunderstorms. And the thing about synoptic thunderstorms is that they can continue right through the night. In fact, those thunderstorms that we saw earlier that are going to be developing, that are developing now over West Texas, will continue right through the night into the Dallas area, down around Houston, and it'll still be raining in Louisiana tomorrow morning. Those are synoptic thunderstorms. Not to be confused with diurnal thunderstorms, which pop up during the heat of the day and then they dissipate once the sun goes down. Synoptic thunderstorms, they continue all night long. The third type is a kind of intensity. If a thunderstorm reaches certain levels, in other words, it will produce hail that's 1 inch in diameter. Not just half inch, not just pea size. It has to be 1 inch in diameter. It used to be 3/4 of an inch until 2007 when the rules changed. So 1 inch in diameter hail, or a convective wind gust to 50 knots or higher, or tornadic activity. So these three things right here, that makes for the third type, which is a severe thunderstorm. Now you may wonder, can a severe thunderstorm happen from a diurnal thunderstorm or a synoptic thunderstorm? The answer is yes. And there's a fourth type of thunderstorm that we're going to get into in a couple of seconds here. But if any thunderstorm reaches this intensity, one of these three, or all of them, then it is a severe thunderstorm. So 1 inch in diameter hail, 50 knot wind gust from the thunderstorm, or tornadic activity. That's
This might be a personal question, but you know how there's like tornado chasers, right? Have you ever had any relations with that?
Yeah, I am a tornado chaser. In fact, I've been doing it for 50 years. In fact,
Oh, okay.
I have video that I can show you. In fact, this could be me down here. Yeah, I do this all the time. We haven't gone out yet this year. My wife and I, we've been married, believe it or not, Ivan, for 49 years. And for all of that time, most of that time, except when we were in Alaska, we would go out and chase tornadoes. In fact, when I was in Omaha, Nebraska at Global Weather Central, I was a severe storm forecaster in the late 70s. We had small children and we would put them in the back of the car and go chase tornadoes. So I've been doing this for a long, long, long time. Yeah, I'm a tornado chaser. In fact, maybe I'll even show some video of the last tornado that I saw. That was near Fort Stockton. It was a couple of years ago. In fact, now that I think about it, now that you bring it up, it was exactly 2 years ago today. It was May 1st. That's when it happened. I'm glad you brought it up. Okay, so that was the last time I saw a tornado. So anyway, tornadic activity will also be considered a severe thunderstorm. Finally, the fourth type, here it is a tropical thunderstorm. And how is that different from all the other thunderstorms? Well, it is just chock full of moisture. Intense downpours over 5 inches per hour. Tops of the thunderstorms to 80,000 feet, which is way up into the stratosphere. And of course, it's the initial phase of tropical cyclones. So yeah, tropical thunderstorms are a big deal. And we do get tropical thunderstorms in California and Arizona in the monsoon season. The monsoon season is usually right around the first part of July through mid-September. And monsoon means that the winds, which are normally out of the west, shift and they become more southeasterly. And the winds across California and Arizona, they bring in moisture from northern Mexico, and we get these intense downpours and flooding and a lot of lightning and all that stuff from tropical thunderstorms. So once again, there are 4 types, and let's go over them one more time. The 4 types.
And tornadoes aren't thunderstorms, like they aren't thunderstorms. They're just a part of severe thunderstorms, correct?
A tornado is well, okay. So tornadoes, how do tornadoes develop? So here we have the ground, we have a thunderstorm up here. Remember that tube I talked about? That tube that we were talking about, the spinning, is a clockwise, is a counterclockwise.
Right. Yep.
The tube is then lifted straight up, and we have in the middle of the thunderstorm, the tube. This is the major updraft. Well, across the top of the tube, we have a very strong jet stream, and the jet stream will grab onto the top of that tube, the same one we talked about, it stretches the top out. And when the top stretches out, that causes the bottom to stretch out to maintain the volume in that tube. And this is that tube. This is the bottom of the tube where the top of it is being stretched out. So all of the wind just simply, it's like a big vacuum cleaner. It's just sort of sucking things up. So
So
that
then
is,
tornadoes are then thunderstorms in.
oh yeah, oh yeah, yeah.
Okay.
You generally will not have a tornado if you don't have a thunderstorm. Now you can have things like dust devils, and that's really not the same. Tornadoes are different from dust devils because tornadoes start at the cloud and they build down. Now the winds are all blowing up into it, but the tornado itself builds down toward the ground till it contacts the ground. With a dust devil, it starts on the ground and goes up into a clear sky generally. That's the difference between those. Then don't forget the tropical thunderstorm. There it is, which is, so what are the 4 types of thunderstorms? Ivan, go ahead.
Okay, we got severe, we got tropical, we have the day job one, and then we have the all night one.
Yeah, the day job one is the diurnal. I like the way you characterize that. The diurnal is the day job one, and the all night one is the synoptic.
Right.
Diurnal, synoptic,
Okay.
severe, and tropical. Those are your 4 types of thunderstorms. And of course, you can go to the Storm Prediction Center page. That's spc.noaa.gov. That's spc.noaa.gov. And get all the information. We were on that earlier. Here you can see the convective outlooks, and they also issue a tornado and severe thunderstorm watches. And we saw one here. You can see that. They also issue things called mesoscale discussions where they can talk about what's happening in the air, and they'll give you the probability that a watch will be issued. In this case was 80%. And of course, we have severe storm reports. We can look at those as well, and this goes back for decades and decades. We've been looking at the mesoscale analysis, which you looked at earlier, and of course, there is the precipitable water. Here's a 500 millibar chart, and here is another look. So all of these things are usable, and we saw them today. So here's a radar mosaic, and in this particular case, it all seemed to be happening in Texas as well. And of course, convective SIGMETs, that's another big thing that are important when you, in fact, we'll look at those in just a moment. That is the end of today's class. So what you need to do is look at the weather handbook there from the FAA, chapters 19 and 20. Check out a lightning video. In fact, we kind of talked about how lightning happens. And then next time, we're going to talk about general weather hazards, and that would include turbulence and icing. But before we do that, let's see, I wanted to also, let's get out of this, and we won't save that. Let's see, what were we looking at? We were going to look at something here. Oh, yeah, SIGMETs. So if we go to the aviationweather.gov site, we can come over here and we can look at where the SIGMETs are. We'll come over here to this, and we'll just turn METAR off and SIGMETs on. So there are the SIGMETs right there, and you can just click on the SIGMET and it'll tell you. This is SIGMET 93 Charlie from southeast of Wink to Midland to Fort Stockton, this whole area right here, an area of severe thunderstorms moving from 240 at 10, tops above flight level 45,000, hail to 3 inches, and wind gusts to 70 knots possible. That is a convective SIGMET. Over here, we have, it's not quite as bad. It's not severe. Developing area of embedded thunderstorms, moving little, tops to 28,000 feet. And yeah, SIGMETs. Of course, there are SIGMETs that are other than thunderstorms. Let's see, do we have turbulence anywhere? Here's some icing down here. And this icing, we're talking icing, let's see here, from 14 to 20,000 feet stationary. That's issued by your good friends in Brazil. So these are SIGMETs, which are very, very important to aviation, as I'm sure you probably know. All right. Okay. Are there any questions, any further questions you have about anything, Ivan?
Uh, this one, not particularly to the lesson. This one was just just a question that I had. It was
Okay.
related to the test.
Okay. The test that we
Okay.
took?
Yes. Last week.
Yes.
So there was a question that mentioned like which one of these gases has the most impact on our atmosphere, right? And I knew it wasn't the other two.
Oh, you mean which was the most impactful for the greenhouse effect?
Yes. On
Sure.
our atmosphere.
Right. You probably said carbon dioxide, right?
Yes.
Yeah,
And I
that's not
understood, right, but I've come here to bargain, you know. I've come here to it- regardless, I'm probably like
this one right
99% wrong,
here.
but
Of the following atmospheric gases, which is the
yes,
most impactful? Yeah, the
yes,
answer is water vapor.
yes. And all right, here's my hypothesis, here's my argument.
All right.
Um, so from what I understand, right?
Hmm.
We emit carbon dioxide, right? And I know that like water vapor comes from like the plants. The 70% of our Earth is filled up like water. Like I understand like a lot of of it comes from water, right? But in
Yes.
theory, if we get rid of the water and we emit a whole bunch of carbon dioxide, it would have a huge impact on the atmosphere.
If we got rid of the water, did you say?
Yes. Like if we oversaturated with carbon dioxide, right? And we just made it so hard uh for the water vapors to do their job, right?
Uh,
It
yeah.
couldn't in theory the carbon dioxide do more damage to the atmosphere than water vapors if we did it.
No, that's just really not that. First of all, we can't do that. In fact, everything is in a balance right now. That's the whole thing. The reason water vapor is more impactful is because there are more of these little spots right here
Mhm.
where the absorption of long wave radiation is thermogenic. Thermogenic. It creates heat.
Right.
Carbon dioxide only has one, two, three spots. And so you can see, and then this is completely pegged right there once you get up to about 18 microns. So there's much more impact from water vapor than there is from the three little peaks there of carbon dioxide. And there's much more water vapor than there is carbon dioxide. Water vapor can be up to 3 or 4% of the atmosphere. Carbon dioxide is 0.04% of the atmosphere.
Right. But if we released enough carbon dioxide, couldn't that overtake it?
No, I think what would happen, and we don't, because the carbon dioxide is absorbed into carbon sinks. Most of that is in the oceans, of which 70% of the Earth's surface is oceans, and then
Right.
it's also absorbed by all of the plants in the jungles and the forests and all that. All of the plants need the carbon dioxide, and they will drink that stuff in.
Uh,
Carbon dioxide is not
us-
a pollutant, regardless of what anybody has told you. And you can believe me or not believe me. That I don't care. I'm just telling you the facts, and you should look at it. And I can tell that you probably do look into this on your own, and that's the best way to learn things. You figure it out for yourself, because
uh,
I can lead you to something, but you've got
uh,
to. People believe what they want to believe, and so I'm telling you that what
okay.
what what it is here.
Could you repeat it? My internet like it went poor, so I didn't catch any of that.
Okay, all you need to know is that water vapor is much more, you can see it, visually right there. That
No,
water,
but why won't the carbon dioxide overtake the water vapor?
because it is being absorbed by plants, and there are many
Right.
more plants in the world than there are animals. And so all of the jungles in Brazil and Africa and Indonesia, all of the plants, they need carbon dioxide for their photosynthesis. And so,
And if there, what if there wasn't as many plants?
well, then there would be a little bit of a change there, but that's not ever going to happen. There's plants in the water. There are plants in the southern and northern hemisphere that do all.
Mm,
You're thinking that all of the fossil fuel
mhm.
exhaust is going to overwhelm the world. Is that what you're thinking?
Yes, yes, yes.
That's just not true. It
Okay.
never has been true, and it won't be true. And even if the carbon dioxide levels do go up, that's due to warming of the oceans. The
Huh.
oceans are warming up a little bit, and they are releasing some of that carbon dioxide that is in the oceans. They
Huh.
release it in the same way that if you warm up a carbonated drink, a fizzy drink, you warm it
Hmm.
up, it's not, it gets flat. It gets flat. It is much. It'll hold the gas, which is carbon dioxide, by the way. If you drink a Coke or a Pepsi or something like that, that's actually
Right.
carbon dioxide. It's mixed into the liquid. When it's colder, it is more able to mix in that gas. But as things warm up, the gas is liberated. So as the oceans warm up, they liberate carbon dioxide. So
And
here's the thing that you and so many other people probably have this wrong, and that is more carbon dioxide causes warming, when in
mhm.
fact it's just the opposite. Warming causes more carbon dioxide.
Warming causes more carbon dioxide.
Yes, because it's a thing called oceanic outgassing, because
Uh-huh.
the water is a little warmer, and then the carbon dioxide, which is mixed into it, is released.
And then that carbon dioxide just when it releases, does it go just back to the atmosphere or just to space? To where does that go?
It goes back to the atmosphere, but the carbon dioxide is a good thing. It is not a bad thing, because plants
Okay.
need it. And we have the symbiotic relationship between plants and animals, where the plants need carbon dioxide for photosynthesis, and we give off carbon dioxide. That's part of our metabolism, but they give off oxygen. That is part of the byproduct of their photosynthesis, and we need the oxygen. So
So then
plants and they work together.
so then when I choose the plastic straws, that's a good thing over the paper straws because it's good to release carbon dioxide then.
Well, plastic, that's a whole other story. You're
Okay,
all
okay.
I'm saying is
What I
that
meant is just
carbon dioxide is not a pollutant, regardless of what
okay.
anybody tells you. It's
Okay,
a
so
good.
then carbon dioxide is not pollutant, it's a good thing then, right?
That's right,
Okay.
because it's part of it's sort of like cholesterol. People want to have less cholesterol in their food, or something like that. But you need a little bit of cholesterol just to form veins and things like that. So if you completely
Mhm.
get rid of anything, it'll throw the entire balance of everything in the universe off kilter. So you need a
Like,
little bit of cholesterol in your body. You need carbon dioxide in the atmosphere. This whole idea that carbon dioxide is just totally bad is just, I don't know. I don't know where people get that stuff.
I think it has
All
to
right.
come from the fact oh, okay, never mind.
All right. I'm going to have to go because I have an appointment here at
Yeah.
1:30
Oh,
with my good friends at Apple. I have a brand new device, and we're going to get that thing going. But this was a very good discussion. I
okay.
really enjoy talking to you. You do a great job there. Are you
Thank
in
you.
Bakersfield, by the way?
Yeah, yeah. CAU, Bakersfield.
Okay, good. Well, hopefully you'll watch me on television tonight on Channel 29 and come on at 5 o'clock. Okay.
Okay. I'll
All
try
right.
to see you.
All right. We'll see you next
Yeah,
time, then. I'll look for
yeah.
you on Wednesday. Okay. On
Okay.
next Monday, rather.
Wednesday.
We'll talk about
Yeah.
turbulence. All right.
Okay.
Thanks so much. Bye bye.
See ya.